All right, howdy. I'm Mr. Justice, and we're going to talk about population characteristics. Let's get started. All right, so you see a picture here on the screen. This is a population of zebras. A population is a group of organisms that belong to the same species. And when we have more than one group of organisms that belong to the same species, we have a community. You can see here in this picture, right? And oftentimes we don't always necessarily include the plants as part of this community too. And they sure are, in fact, right? It's not just the animals, the birds that you see here in this picture. It's also going to be the plants and even some of the unpictured organisms that we can't see, like the bacteria and decomposers or fungi that might exist in there that help decompose the matter back into the ecosystem. So what determines a population size? Well, the inputs and the outputs. What can input into a population? Individuals that are immigrating into the area, and births will increase population size. But there are also some factors that can decrease population size too. That's going to be emigration, movement away from an area, and deaths. The California condors, the population size was pretty low in the 21st century. And so, in an effort to increase the population size, ecologists created a captive breeding program in an effort to increase the inputs, the births of the population of the California condor. By 2018, they were able to increase the population size of the California condor all the way up to 488. Right? Increasing those inputs while ensuring that the deaths aren't happening as a result of unnatural processes will increase that population size as a result. So let's make a little concept map about population characteristics. They include the ratio of males to females. We'll discuss this in relation to human population studies. Right, but the idea is that well, the ratio of childbearing organisms that are able to produce life will impact the population size. Right, if you have more males than females, you might not necessarily see an increase of the population as readily as if you had a population that had more females to males. Right, or a more even ratio too. Age structure is another population characteristic that we talk a little bit more about in our studies with human populations. Age structure is important because, especially in humans, there is kind of a range of reproductive age, right? Of reproduction that could happen. Individuals that are older are unable to, increase births just as much as individuals that are younger are unable to increase births. So there's kind of this narrow band of opportunity, we'll say. And we'll talk more about that in our human population studies. Population size can be estimated by a process called capture, mark, recapture techniques. They can be used to try to estimate the size of a population. And I'm trying to work on a simulation that we can do in class to kind of do this process to see what it's like. Population density refers to the number of individuals per unit of area, and we'll talk about that in a moment too. Population distribution, the way that individuals within a population are distributed throughout the ecosystems, is also something that's important. There's two different distributions or dispersion patterns. There's random distribution or dispersion, uniform, and clumped. And this is what it might look like. Those green dots represent living organisms. The clumped individuals tend to clump up maybe around limited resources. Uniform distribution might exist because of chemicals that are secreted by maybe, let's say, plants, like in the case of the creosote bush here in the Las Vegas Valley, secrete chemicals into the soil that prevents the encroachment of other plants from kind of taking their spot on the desert floor, for example. Then random distribution we might see as a result of random seed dispersal, or even just maybe coyotes or wolves that kind of belong to a specific territory. A little bit more information here, some more examples too for us. Here again is that clumped dispersion pattern or distribution pattern. You have to kind of imagine, right, that maybe those sea stars or the barnacles are clumped in this specific pattern because there is food available there, right? Some limiting resource like maybe habitat, space, water in some cases, or foods. These sea stars might also choose this space because it is close enough to the intertidal zone. It doesn't want to be, the barnacles and the sea stars don't want to be dried out, right? So they're kind of limited as to the number or the where in the rocks they can actually attach themselves to. This is an example right here that you're seeing of penguins that are dispersed and distributed pretty uniformly. The reason for this is an effort to protect their young. Take a look here. The last one is, there we go, making the computer go, is random dispersion. We're going to see this oftentimes with maybe random seed dispersal, right? There's no rhyme or reason as to why a seed might implant in the soil that is carried by the wind, right? It might end up here in this area just as much as it might end up further back in the picture. It's random, and so therefore that life then will sprout up in random spots. Population density, right, is that characteristic that refers to how crowded a population is in an area. I'm looking at the picture right here, right? We've got a lot of people packed in to a small space. We can express this then as the number of individuals per unit of area. Got an example here on the board, 30 people per square kilometer, for example. I usually have about 40 students in each one of my classes, and so we can say, well, there's 40 people per 600 square feet of classroom, as an example, right? What might it look like here for in different areas of our world? Like in Macau, about 6 square miles of space is all, but there's about 400,000 people that live within that area. So there's about a 55,000 people per square mile, right? Think about the implications of that. We're probably building up rather than out in this specific place. Here in Las Vegas, we've got about 4,376 people per square mile, which is a lot more than the United States in general, right? 93 people per square mile. Give me a moment. I'm going to pull up a picture here that I'm just going to find online. All right. So this right here is the distribution of the citizens here that live in the United States in 2010. So think to yourself for a moment, what kind of distribution or dispersion pattern are you seeing? Take a moment. You probably might say clumped, right? And that would be true, right? Think about all the different resources, the jobs, right? The availability of temperate weather in some of these areas that have darker colors. Those darker colors on this map indicate that it's a more dense area. There's more individuals in there. Look at New York up here, right? Lots of job opportunities maybe. So in humans, we kind of talk about those limiting resources a little differently, I suppose. But the point is that we've got some clumped distribution. In addition to, like I mentioned earlier, there's 93 people per square mile. So there's a lot of people in some of the places, right? And then there's not a lot of people in a lot of the other areas too, right? In these areas that show up that are lighter colored, fewer people per square mile. So it's a large place, and we're all kind of congregating in certain areas of our country. So how are populations, not human populations, but how are populations of animals and plants controlled in the wild, right? Population control. Well, there's this idea here that there's this density-dependent population regulation process that happens. The size of the population will influence an individual's probability of survival, and large populations are at a greater risk. Think about, let's break down density-dependent population control. The population size is controlled based on the number of individuals in an area. So think to yourself for a moment, okay, well, why might the population decrease? It might decrease because an increase of deaths. Well, think about why an individual in an ecosystem might die, right? Maybe there's competition from some limiting resource. If you have a lot of individuals in a small space all competing for resources, food, nutrients, space, right, land, habitat, water, well, only the fit will survive. Predation is another way that the population can be controlled. Hey, if you have a lot of predators in the area, then you're going to decrease the prey, right? Because the predators will eat the prey. We saw this happen with those ties snails simulation from earlier when we talked about the barnacles in those snails in that intertidal zone simulation from earlier in the class. Predation can either decrease or increase a population. If there aren't a lot of predators, population sizes of the prey will increase, right? Hey, disease and parasites are also density-dependent population regulation processes. Hey, think about the cattle right there, right? The cattle, the closer they are to one another, the more densely packed this population of cattle are in an area, the more likely that they might transmit a disease from one another. They're touching each other, they're in their airspace. Compared to maybe an area that has fewer cattle, less transmission as a result, right? So the population can either go up or down depending on how it's being regulated. Waste accumulation kind of goes hand in hand too with disease and parasites, but waste is going to take up habitat space. So if we are using up habitat space that could have been used for living rather than for our waste accumulation, then there's going to be less individuals that can exist in that area as a result, right? And access to those limiting resources is absolutely density dependent, right? Competition for those resources like water, food, nutrients, habitat are going to impact population size too. So just as there are density dependent population controls, there are also density independent population control. So there are other ways then that population of organisms can decrease in size, and that could very well be likely caused by natural events. Right, fires can wipe out an entire stand of trees, and that will happen regardless of how many trees exist in that area. Likewise, there are other animals and deer that might live in this area too. So it didn't matter if there were 1,000 deer or 100 deer in a fire. A wildfire is going to displace all of them regardless of the population size. That's why fire is considered density independent population control, right? We're controlling the population independent of its density. A big tragedy like a fire or a flood can do that, right? Floods can wipe out the topsoil of an area and decrease the amount of vegetation and plants that then can grow there, right? And that happens regardless of how many plants were there prior to the flood coming through. Earthquakes, hurricanes, and volcanoes can also destroy habitat or displace animals or destroy plants, right? And that happens regardless of how many of those individuals there were, right? Because it's density independent population control. The population decreased independent of how many individuals there were in the area. Drought is another one, right? The wildfires in California likely caused by drought conditions in that area. And right, so the more likelihood of having a decrease of water, it doesn't really matter how many plants are being impacted by this. It's just that it's impacting all the plants regardless of how many there were. All right, so in the module today, what you're going to do is go through a case study that discusses the transmission of the rinderpest virus from cattle and wildebeest living in the Serengeti, right, a savanna area in Africa. And so as you go through that simulation, or rather that case study, I want you to really think about density-dependent population regulation and density-independent population regulation. And think to yourself about this question, right? How did the eradication of a virus that infects cattle in Africa lead to an increase in tree growth, right? So how are these two connected right here? You guys are going to learn a little bit about that through the case study. You're going to look at some graphs. In fact, the graph is going to look like this. So when you get in here to the case study under Canvas, under day 7, I want you to really look at both of the y-axes, right? Notice that prevalence of rinderpest in the wildebeest population is going to be the scale on the right side of our graph, and the wildebeest population themselves in thousands will be in the left y-axis over here. All right, and just know that this line, the line with the circles that are colored in, this represents the population of the wildebeest, and the other one, it represents the prevalence, how common it is for rinderpest to be impacting the wildebeest in the area. All right, rinderpest is killing off these wildebeest. So is rinderpest virus, is it density dependent or density independent? Push pause and work on this simulation or this case study, and we'll go over the answers in a moment. All right, so let's go over the answers. Question 1 was, what are some of the possible factors that could cause an animal population like the wildebeest to increase? Think about more births or more immigration into the area. In the case of wildebeest, they're probably, if they were going to increase, they have access to limiting resources like water, food, and habitat space. There might even be a decrease in predators in the area too, right? Plenty of resources to go around to decrease competition. Those are all ways to make a wildebeest population increase. If you answered out question 2, describe the trends in the wildebeest population over time, I would say, hey, this line, the one with the black circles, represents the wildebeest population. It looks like the population of wildebeest grew exponentially over the course of the 1960s into the 1970s, and then it looks like it kind of started to slow down getting into the 80s, 90s, and 2000s. Question 3, what was regulating the wildebeest population before 1960? Is this a density dependent or independent factor? Explain. Take a look, right? Prior to 1960s, right down here, the population of the wildebeest was pretty low. Why? Well, there's probably going to be some connection between the prevalence of the rinderpest. The rinderpest was killing the wildebeest. Look at the prevalence of it, right? About 90%, almost 90% of the wildebeest have rinderpest. Now, in the 1950s into the early 60s, there was an inoculation, a vaccination process that happened so that the prevalence of rinderpest decreased pretty substantially over the pretty short amount of time. But we'll talk about that in a moment. I'm kind of getting ahead of myself. This though, guys, that prevalence disease is density dependent. All right, so if you've got a large population of wildebeest in an area and there's disease that can transmit between the different wildebeest, it's going to keep that wildebeest population down if that disease is killing them. Question 4, what is the connection between virus prevalence and wildebeest population? Use the evidence in the graph to support your claim. So we're going to talk about a relationship here, right? So we're going to talk about both of these lines here. As the prevalence of the rinderpest infections decreased, the population of the wildebeest increased. I know that because between 1960 and 1963, the prevalence of rinderpest decreased from 90 degrees to 0 degrees. And by degrees, I mean percents, 90% to 0%. Whereas between 1960 and 1980 or so, the wildebeest population increased from 200,000 to over 1.2 million individuals. Question 5, based on the trends in the graph, what do you think the approximate carrying capacity for the wildebeest population is? Why do you think this is? This area right here, so right, take a look. After the eradication of the rinderpest, hey, the wildebeest population was free to grow, right? But then there were some other resistance that was kind of slowing down and preventing that population from growing forever into the billions, right? Well, what it is, what is it, right? What is the carrying capacity? It's probably going to be the average between all of these lines here. So once that line starts to even out, right, what we would do is we'd kind of like interpolate in between all this data and draw a line all the way across. We'd say that the approximate carrying capacity of this area is probably 1,200 thousands of wildebeest, or 1.2 million wildebeest. After the rinderpest was eliminated, the wildebeest population increased exponentially until the 1980s when the population stabilized. This is what I was talking about previously, right? Why did it stabilize? What were those factors? Are they density dependent or independent? Well, why did it level out? Access to those limiting resources. There could be predators in the area. There could be competition. There could be another disease or waste accumulation. Anything that could prevent and slow down that input of the population, right? We're decreasing the inputs, so we're going to decrease then the population size as a result. How is it possible for a virus to affect tree density in the Serengeti? As you increase the wildebeest population, you're increasing the eating, the herbivory that's happening in the area, right? These guys are herbivores. They're eating the grass. Grass burns in a savanna normally, right? So if you increase the population of wildebeest, you're decreasing the population of the grass, the flammable grass. Because we've got less fuel for the fire, we're decreasing fire, and as a result, we increase tree density because, well, trees aren't now being controlled by fire. If we take away the fire, then we increase the trees. So which ones are density dependent and which ones are density independent? I would say that the relationship between wildebeest and grass is absolutely density dependent. That grass decreases in population size because of all of those mouths, all of those wildebeest that are now eating it. Hey, fire, right? Fire is a natural process. And so that tree density increase is kind of being controlled by a density independent process. Kind of interesting to think of it that way. Finally, question number 8. If you watched the video at crjust.s/rinderpest, you would have found that an introduction of the rinderpest virus into our world, again, would wreak absolute havoc on our economies. Prices of meat would go up, people would be displaced from work, and it would be pretty bad. So luckily, though, the rinderpest virus is put away in a science lab, never to be seen again. That sounds like the beginning of a horror movie. Anyway, I hope you enjoyed the video, and let me know if you have any questions.